Now factors, what is basic strength? Matlab a compound which can, I'm talking of Lewis base, which can accept as a proton acceptor, or indirectly I can say can act as a lone pair donor, will be called as base. And as we were comparing yesterday, acid strength, that how easily they can donate proton, same way today we'll talk of how easily they can accept protons and thereby becoming conjugate acids. Okay, that is what we are looking for here. So factors affecting basic strength of base, how to decide. I'm here not talking of any particular organic or inorganic or anything. I'm just taking in general start. So ease of lone pair availability and donation is the most important factor, that how easily this B can actually donate the lone pair and accept the H plus. That is our first consideration for a compound to act as a base. Okay, whether they will act as a good base or not. I see certain hands raised. There must be issue, I assume. Otherwise, Abhito, I have not yet started. Yes, Akhila, speak.
Ma'am, the screen is like stuck in Narayana Zoom.
Oh, is it? Okay, okay. I'll reshare. Fine. Something is wrong. Is it
Yes,
now?
ma'am, it's visible right now.
Okay. Thank you. Thank you. So let me start again. So we were talking that we have to compare base as a strength. So what we will be talking, or how to compare compounds basic strength. Now in yesterday's slides, I have already discussed what is acid, what is base, how to define them as acid and base. But now ease of lone pair availability or capacity to donate that lone pair will decide whether a compound is a good base or a bad base, or a comparative set when questions, you know how it comes, right? So first factor, how to decide this whole thing. So donor less electronegative, then definitely it is going to be a better base. That is one of the factors. I'm not saying that is the sole factor. Okay, for here I can say this is the factor. Now why I'm so precautious about my statement, because in Lewis basicity of ammonia, phosphine, arsine, ammonia is a better Lewis base than phosphine. Okay, in reaction of alkyl halides with AlCl3, where alkyl halides act as a Lewis base, RF is a better Lewis base. So more electronegative there are better Lewis base. There we talk of high electron density on fluorine, high electron density on nitrogen, and thereby they are acting as a better base. That is the concept we use there. Okay, so that is why I'm not generalizing that always as a rule this could be true, but yes, for organic compound, when the donor atom is same, then this hybridization thing is valid. Okay, so how it goes, more the percentage S in the donor atom, bad base it will behave. How to check that? Why it will be a bad base? So I can simply say that it will be a bad base because if I form CH3, CH2NH2H plus, and we have an equilibrium. So CH3, CH2, NH3 positive, and CH3C triple bond N. When I donate H plus to this, so CH3C triple bond NH positive. Now here the positive charge which is coming is on high electronegative nitrogen, or I can say the nitrogen with higher S. So this is getting unstable. If this is becoming unstable, equilibrium is going backward. Equilibrium is going backward, making it a bad base. Now, whereas when I talk of ammonia and say phosphine, Here the story is a little different by the same logic, of course. I have NH4 plus, but the atoms are different. है ना? For here I have PH4 plus. Now phosphorus hydrogen bond being weaker, so this goes backward. This bond dissociation energy is lesser than nitrogen and hydrogen bond. So when this goes backward, this is becoming a poor base than ammonia. So similar thing, but see how it is used, how it is affecting the basic strength. Okay, this is how we are comparing. First thing, percentage S character when the donor atom is same. Percentage S character when the donor atom is same, then I can say sp3 is a better base than sp2, then sp. Okay. Next factor is the stability of the conjugate acid formed. Now see if I compare amine versus amide. My conjugate is RNH3 plus. This is the best approach to solve the basicity order cases. Always form the conjugate acid and compare the stability. So RNH3 plus. As you all are aware that once this NH3 plus is formed, here nitrogen's octet is complete. Right? This nitrogen's octet is complete. So it cannot do any resonance. Here also nitrogen's octet is complete, cannot do resonance. But here R is attached directly, which will act as a plus I group. Here acyl group is attached. This will act as a minus I group. And minus I group will definitely destabilize this conjugate acid formed, resulting in amide being a weaker base than amine. Right? So what approach we will do? We will form the conjugate acids and compare their stabilities, and then we'll decide how to use it. Is that absolutely okay? Then comes, in certain cases, we will be using flipping. Flipping is something which is very, very limited case. How to use and where to use. See, flipping is a phenomena which is characteristic of tetrahedron molecules having one lone pair. Okay, tetrahedron, one lone pair, and that too on second period central atom, not any. Okay, it has to be compulsorily on second period central atom. When the second period central atom is there, then what happens? See, this is an sp3 ammonia. When it inverts, okay, nitrogen from sp3 going to sp2, again it is converting back to sp3, and there is equal probability that it goes upside or it goes downside. For example, I have these 3 pens in my hand. I hope visible, right? So, and the lone pair is here. This is my lone pair. Okay, this is my lone pair. If I form this, now it goes to sp2. So all will come to plane. This will become like unhybridized P. And then this will go down and all will go up again. So what is happening? As a result of this flipping, the lone pair availability at one spot is not fixed. It is moving here and there. And if I talk of just ammonia, it is 10 to the power 21 times per second, like a very fast speed fan. And due to this flickering or a flipping, the lone pair is not located at one spot. So when proton attacks, the probability of hitting the right orientation to form the conjugate acid is decreasing. Even if flipping, I assume, is decreased, something which is 10 to the power 21 times, even comes to 10 to the power 10 times, is still way beyond the situation that I can say it is not affecting anymore. It will always decrease the basicity, increase the stability in case of carbon ions. Okay, because as I said, second period hona chahiye central atom. Central atom should be from second period, should have a tetrahedron, okay, geometry, and should have one lone pair. That is what we want. Is that absolutely okay? So flipping ultimately is decreasing the basicity. When should we use flipping for comparisons? Only when in a question use flipping when one of the molecule has zero or no flipping and other has flipping. Never ever use flipping for molecules ki one is having more and one is having less. That is of no importance and that will always mislead you. Okay, use flipping for comparisons only when there is inhibition, or I should say stoppage of the flipping. And when does flipping stop? Flipping stops when your nitrogen is at the bridgehead. Okay, compulsorily it should be at a bridgehead. And this is a very famous base called quinacridine, in which the nitrogen at bridgehead is present and the flipping is inhibited, is stopped. So this will be a better base than the comparative open chain structure in which flipping is decreasing the basicity. Is that okay? Moving further, now we'll limit ourselves to particular organic bases. So in case of organic bases, I'll talk one at a time and we'll try to be very much oriented as for questions. Okay. So according to question, we'll be oriented. So let's start. First thing first, if I talk of organic bases, then the one which comes first into our brain is certainly amines, right? And in amines, what to take into importance? What is the important part that you have to consider? Of course, conjugate acid formation, as I have told, you will form such conjugate acid. Now, if you compare these conjugate acids in gaseous state when there is no solvation, no support of solvent, just gas, then of course there is only one factor which is stabilizing these conjugate acids, and that is the plus I of these alkyl groups. More the plus I, better will be the stability of N plus, and thus I can say using plus I, right? The order of stability of conjugate acid is 3 degree better than 2 degree better than 1 degree. Ammonia is the least, there is no plus I. Okay, so in gaseous phase, when there is no other factor, in fact, the order of basicity of different amines is found to be so. We have found this only. Whereas in water, this cannot be the sole factor for stabilizing the conjugate acid. Then what factor will come into scene? The solvent effect. If I talk of water, these amines have two parts, right? Two parts. Say, for example, if I say R NH3 plus for primary amine I am talking, then this whole part is acting as hydrophilic. Is that correct? This part is acting as hydrophilic because this is capable of forming hydrogen bond with water. Is it correct? It will form hydrogen bond with water. So water will surround it, will stabilize it. Whereas this part, which is the alkyl part, this will be repulsive for water and we'll call it hydrophobic part. Okay, now it all depends that what is dominating. But as I can clearly see, in case of 3 degree alkyl, I have 3 alkyl. 3 degree amines, I have 3 alkyls. In 1 degree amine, I have 1 alkyl. So with more the number of alkyls, hydrophobic part dominance is increasing, right? So H bonding will support 1 degree amine as a better dissolved And dissolve matlab solvation energy is released, hydration energy is released. So that will make the equilibrium forward or support the forward equilibrium is a better terminology. So I can say that if I talk for solvation factor with water, 1 degree amine is better than 2 degree, then 3 degree. Now you may say, what about ammonia? Ammonia still is not that strong because overall we need a combination of both plus I and H bonding. Now, if I talk of observation, if plus I would have dominated, okay, we assume, okay, both are there, but if I say ki, which will be finally conclusive to be strongest of all, if plus I would have dominated over H bonding, so I would say ki 2 degree to anyhow is best because it is like neither too pushed away or supported by either, somewhere in between. 2 degree is okay, but if plus I is better, then the next number will be 3 degree, then 1 degree, then ammonia. In case of H bonding, it is 2 degree, then 1 degree, then 3 degree, then ammonia. Ammonia is anyhow is the least. Right? Now, what is the observation which is going to be strongest? So answer is when R is methyl, we find that order is 2, 1, 3 and then ammonia. When R is ethyl and onwards, then the order is 2 degree, 3 degree, 1 degree and ammonia. I would still say don't generalize it. Why I would still say, let me take you to the NCERT page again. These are the nitrophenols. Here is the amine. Okay, here is the amine case. And let me share what I want to discuss. Let us discuss this thing. That what we have decided 1 degree, 2 degree, 3 degree and all these factors. I'll take this part from here to where we were discussing our factor here. So see, let me see whether this thing is coming in sync with the NCERT data or not. It is extremely important for us to conclude. Methenamine, okay, 3.38. pKb is given. So I'll go for reverse. High pKb, it will be inverse to Kb and thereby is inverse to basic strength, basicity here. है ना? So I'll say higher pKb, poor base, right? That is what it appears. And pKb values of amines in aqueous phase, it is clearly mentioned. Okay? So let us see Me3N 4.22. Okay, 3 degree methyl. Let me write 3 degree and methyl. Here pKb values as per NCERT. Me3N is 4.22. Me3NH2. Again, I would say it is not very appropriate to go by this method as the carbons are changing. They should somehow be quite isomeric. Then it is better to say, but okay, continue karte. This is 3.27 and for 1 degree it is 3.38. Okay, so 2 degree, then 1 degree, then 3 degree. As we said, inverse is the relationship, right? Let us go for ET, ethyl. Again, let us check. ET3N, 3.25 it seems. 3.25 for 1 degree is ethanamine 3.29. Okay, higher pKb, less basicity. Okay, and 2 degree, check where is 2 degree. This is 2 degree, 3 it seems. This is again pKb and where we are referring, this is simple NCERT amines chapter table, right? So this is how we concluded that for methyl it is 213, for ethyl it is 231. But I would like to make it a point that this may or may not be valid for higher amines. It may keep on varying the factors. Okay, so general, but if question pops out of the blue, go for this, that ethylene further, take uh, ethylene further 231, and for methyl 213, take this as an order. Is that absolutely clear? Take reference is clear. Moving to next type. Yes, I will take the other part of NCRT. All this we'll consider. Just let us move further. Okay, we have just considered few till now. Now let us talk of amides. Amides, if you see the resonance in amides itself, amides will definitely will have this resonance. है ना? RCO minus double bond NH2 plus. So if you see in the hybrid, nitrogen is having positive, O is having negative. So H plus will be more attracted to oxygen. If I say this structure, one choice, or if I say RCOH double bond NH2 positive, this structure is my other choice. And my conclusion is this will be the preferred. ठीक, amines are certainly stronger base than amides. As you can see that this is the oxygen donor. If you take this, then we have already talked, this is a minus I group. So any which way, amides cannot win over amines in its basic strength. Is that absolutely clear? So amines are always stronger base than amides. And I should write amides prefer to act as base through oxygen rather than nitrogen. And reason is resonance hybrid. Is that absolutely okay? Right? Next type of comparative sets which are important is pyrrole, pyridine, and aniline. We take one individually and then we'll confirm with the pK values. All these pK values here I have taken. We have taken it from, I should write somewhere, Claydon. Okay, these type of cuttings, wherever you come across in notes, they are from Claydon. Okay. So let us compare pyrrole, pyridine, and aniline. Now see, in pyrrole, this nitrogen lone pair is part of the aromatic cloud. 4n plus 2 equal to 6. That cloud includes this lone pair. When I donate this lone pair to H plus, then the resonance will be inhibited and a system which is formed is non-aromatic. If something is coming non-aromatic from aromatic, then certainly this equilibrium is not supported. Okay, is not in favor of forward reaction. Okay, so this is not good. Coming to others, this if I see, here is the nitrogen lone pair and it is a localized lone pair. It is not part of resonance. Resonance is using this, just arrow ka direction I have to change. This type of resonance is going on in this pyridine cloud, right? So this is a localized lone pair and localized lone pair will be definitely better available to act as a base. So this conjugate, it was aromatic, it is aromatic. So we are from aromatic to aromatic. Absolutely okay. Coming to here, if I see this lone pair is part of resonance. Okay, this is resonating lone pair. It is not available at one spot. Resonating lone pair, and it was aromatic. It is aromatic, but the lone pair I need to donate is part of some resonance. Not as important of a resonance as in pyrrole, but still there it is part of resonance. Similarly, if I compare the conjugate stabilities among the three, here, this is a totally non resonance stabilized N plus. There is no support from anywhere for nitrogen. This is resonance stabilized. Okay, because still this type of resonance may come and you will see other carbons will share the charge. Resonance stabilized conjugate acid. Stabilized conjugate acid. Here I see nitrogen plus will not be part of resonance. So it is also not a resonance stabilized. So considering all these factors, it is clear that pyridine is going to be the strongest one, then the aniline, and then will come the pyrrole. Is that absolutely clear? Pyridine, aniline, and then pyrrole. So let us put this data from here. Aniline, pKh. This time in Claydon, the data are given of pKh. That is pKa of conjugate acid. So conjugate acid ka pKa high. pK will be inversely proportional to K of conjugate acid. Right? K of conjugate acid is low. It means I can say ki Kb of conjugate base will be more. Inverse relationship. So pK of conjugate acid is directly proportional to Kb of the conjugate base. Let us say directly put the values. Aniline is 4.6. Aniline is 4.6. What I'm writing? I'm writing pKh of conjugate acids. Pyridine, where is pyridine? 5.2. 5.2. Check pyrrole. If I am reading right, it is -4. Is it absolutely clear? 5.2, 4.6, and -4. So pyridine is much, much better as a base than aniline and then pyrrole. Okay? A very important comparative question. Here, one more thing you note. See, cyclohexylamine. I hope this is clear, but let me enlarge it. Now it will come better on your screens. Cyclohexylamine, pKh is 10.7. Aniline 4.6. A clear reason, localized lone pair, and there is no minus I. In fact, it is a plus I group, right? Combined effect, cyclohexylamine is going to be the best of all these as a base. Okay, so let's move further. Guanidine and amidines. Now, what is guanidine? Guanidine is NH2C double bond NH single bond NH2. Again, by resonance, it will accept its H plus from this nitrogen rather than these two. So the conjugate acid formed is NH2C double bond NH2 plus single bond NH2. And if you draw its resonance, you will get 3 equivalent resonating structures in which octet of all involved atoms is complete, right? So see, here is the hybrid. Here is the hybrid. All 3 nitrogens are participating, and such the guanidine pKa of conjugate is 13.6. Okay, this one's pKa is 13.6. What is amidine? One of the NH2 is replaced by any alkyl. C double bond NH single bond NH2. Then it is called amidine. This could be any alkyl. Now when I accept H plus, of course, double bonded nitrogen will participate. So RC double bond NH2 plus single bond NH2. Taking into resonance, C NH2 double bond NH2 plus. So you will have 2 equivalent resonating structures, right? That type of resonating structures, again, of course, weaker resonance stabilized than guanidine. It has 3, this has 2. But see the pKa of this conjugate acids, pKh is 12.4. So which is a better base. I think till now, whatever you have seen, you have not found any pK higher than 13.6 in our entire list till now. So guanidine is much better as a base than amidine. Okay, I'll just go back to the list and I will make you realize, just wait. So guanidine is strongest, then is the amidine. Okay, see, then was the aliphatic cyclohexylamine, right? Going back to this, if you see, as these are not the conjugate ones, so it is difficult to relate directly. I'll find a list jahan par the conjugate acid strength wise data is given. Okay, so after this comes the aliphatic amine. So whatever is available till now discussed, I'll write like this. Okay, and it is quite important to remember that guanidine is like one of the strongest, I wouldn't say strongest of all organic base, because we are not going into the entire chemistry. We are limiting ourselves to entire syllabus. Syllabus is defined. So I'll not comment that it is the strongest organic base, but I would say it is one of the strongest organic base. Okay, taken screenshots wherever necessary. Moving further, guanidine and amidine we have done. Oh yeah, this was one of the question of JEE 2017. Again, see, guanidine and amidine are there. These two are there in comparison. 2 and 3 we have to see. We'll see. First, out of these, you check that which center will act as a base. So here I will accept H here. Here I will accept H here. यहाँ से H plus will accept. In this one, you will accept H plus here. Right? And here I will accept from this position. First thing first. Whatever the choices out of these, you realize that 4 is going to be the strong anyhow. Okay, 4 is going to be the strongest. So 4 strongest, I have two choices, B and C. So I will remove D and A from my choices first. Always approach this way so that you can zero in better. Okay, so this is done. Now if I want to compare these two with mindsets and how to get into answering, let us compare. So if I, the order of basicity, 4 is the strongest, certainly. And I think it was not B as an answer, it was C. I'll check answer. Once, wait. First, let us solve. Amongst 2 and 3, how to solve? So first 2 and 3, if I check, NH, double bond, and if I form this NH plus, this thing is just resonating with this. It has no other side of resonance. So I can say it is two equivalent RS. Okay, not going here and there. NH and double bond NH, this I am forming for third. So here again, this part is resonating well and good, but this lone pair can go to this side also, no? So this lone pair is resonating two side. And if it is resonating two side, definitely its positive impact on our targeted plus center will be less. Is that absolutely clear? So it should be a relatively weaker base than this one. That is one way of seeing. Another way of seeing, you can simply say this is a plus I group, and this, when not participating or not influencing our conjugate acid by resonance, I would say it is rather acting as a minus I group. So my conclusion, 2 is going to be better base than 3. That I need. Okay, 2 has to be better base than 3. So 2 better base than 3 I am getting in both. Okay, 4 is best, 2 and 3, 2 and 3 and 4 is best. Now I have to just decide location of one. And here datas are also for your final conclusion. See imidazoline, that is this one. pKh is 11. This one is 7.1. So very clear, this is much better base than this. Okay. And it is clear that amidine is going to be strong. So 1 here. But why it is strong? Why I thought that it should be stronger than 2. That I will explain. Okay. Yeah, someone rose my hand itself. How? So how it is going to be, stronger? What could be this answer? I think I wrote incorrect. It should be C. I'll check. Don't worry. ओके आपके साथ ही मैं चेक करूंगी. आप बिल्कुल चिंता ना करें कि कोई एरर आए. नहीं, बिल्कुल नहीं. विल चेक. सो फर्स्ट यू लिसन टू माय लॉजिक. CH3 C double bond NH NH2, this CH3 located here will also have an impact of this type of plus H, thereby stabilizing this conjugate acid by its plus H. I don't see any such support here, right? So I'll say amidine is to be stronger and my data will support. Amidine is 12.4 and this is 11. Yes, it supports. So answer has to be C. Is that clear how I concluded? Right? Amidine is the best. Hybridization wise, all are double bond N. So that point was not there. All are nitrogen. Okay. Now going to the resonating structures. Fourth is best, 3 equivalent RS. Then with 2 equivalent RS, I got 2 choices, 1 and 2. In 1, I had a hyperconjugative CH3 help. In 2, I didn't have. That is how I concluded. Okay. It is 2017 question. Let me just take you to that point. Just, oh, I didn't share the screen, I guess, so that you be better clear that how to go back to my Zoom session. Oh, by this. Okay. Give me a second. Share screen. Screen is shared. Just wait. JE past papers. What was the year? 2017, है ना? But paper 1 or 2 not clear. So I'll open both. Okay, let me decrease the size. And let us go to the question. This is the actual JE answer key. So we need to confirm. Section 2. Here I got 25. Answer is C. Let me get it very clear for you. The order of basicity, C, what it is, 4, yes, then 1, amidine, yes, then 2, and then 3. Yes. Right? So answer was C. C down. Question number 25, answer was C. Right? So I might have just wrote something. Let me reshare my work. Is it coming? It is still screen, I guess. I want open board to be shared. Give me last attempt. Come on. Yes, it came. So answer I changed here, C. This is a very important question. I hope आप गलती नहीं करेंगे. Then comes the anilines में ortho effect. That is also one type of questionnaire. Now in benzoic acids, yesterday we did whatever present at ortho position always increases the basicity of benzoic acid and there is no exception. Whereas in case of aniline, if I apply the same concept, whatever present at ortho position will increase the acidity, right? NH2 versus NH3 plus. NH3 plus is bigger, bulkier. So this will have the steric influence and the reaction will go backward. If the reaction goes backward, the basicity will be decreased and acidity is increased. Okay. So anilines में ortho effect or SIP, steric inhibition of protonation. that anything present at ortho position will make them as a poorer base as compared to contemporary, right? But the exception to SIP, okay, is OME and OH. OH and OME may is steric inhibition of protonation is found to be absent. Okay. Took a screenshot OME and OH. There, I cannot say that it is a general order like less to kitna less or more to kitna more. I'll give you a conclusive order for this. Okay, give me a second. For OME and OH, when the SIP is absent in them, yeah, here. So for OH, the order is para, ortho, reference, and meta. For, okay, I have to add a page here. For aniline, and if I have OH, my way of comparison is by same. What is OH? OH is a plus R greater than minus I group. It will support the basicity. So the final conclusion for this is para, ortho, then aniline, and then meta. See, in meta only minus I, in para and ortho we found plus R and minus I. Okay. Second, in case of OME, if I talk of OME, NH2OME, this is also a problem, but I cannot say exact copy paste to OH. Here it is para, reference, ortho, and meta, right? So yes, there is some effect of steric, but not to the level ki pushed it to the last. And for others, wherever there is this SIP, wherever, for example, if I talk of NH2 and NH2OME, if I talk of, not OME, only ME. If I talk of only ME, then my order should be similar to somewhat that ortho, then para, then meta, then reference, but actual order is para, meta, reference, and then ortho. So here we are observing, SIP, and here SIP absent. Not to the complete extent for OME, but otherwise it is absent. Is that clear? How to use this, right? Okay, let's move further. And sometimes steric inhibition of resonance. Going further, first I'll add here only the factor that rarely but yes, steric inhibition of resonance can also impact the basicity. Certainly, it can impact, and both ways. Like, what do I mean by both ways? For example, if I have NMe2 and then I have NMe2, Me and Me, and Me and Me, right? So I'll say as a base, 2 is going to be 1, say greater, because this NMe2 will have steric inhibition of resonance and thereby lone pair availability is increased, right? That is one way. Other way, that it is not the nitrogen group which is suffering the SIR, but CNH2, Me, Me, and NO2. Now this time this NO2 is having SIR, right? So here what it was doing, it was withdrawing the lone pair. It was part of resonance. Here its resonance is inhibited, it is stopped. So that is why 2 is greater than 1. So yes, steric inhibition of resonance can sometimes do this wonder of increasing the basicity. Clear? Now let us come to the comparison of aziridine and pyrrole. See, aziridine is a 3-member ring in which the percentage S character of this exocyclic lone pair is quite high. Okay, 3-member ring are always an exception. We'll talk for this in future also, but here this lone pair is present in hybrid orbital with higher percentage S than a normal sp3. If you consider it with sp3, that is not appropriate. It is not acting like an sp3, right? So when it forms conjugate, the plus charge will come to a hybrid orbital having higher percentage S. So it is unstable. So that is why, despite being a 2-degree amine, it will not behave as good as a base like any other 2-degree amine. Okay, so pyrrole had a different reason, but I'm comparing the two. And aziridine has a different reason. Now see, this pKa is 8, whereas for pyrrole, we had somewhere here it was -4, right? In case of pyrrole, we had -4. And I think all of you will agree that yes, there is a factor of stability of conjugate and all that. But if we compare these two, then aziridine is stronger base than pyrrole, right? Basic strength, but is much poor as a base than any 2-degree amine. 2-degree amine, then comes these. Is that clear? Right? Then comes these. This is what should be the order of their basic strength. It is creating me. No, it is perfect. Right? So these are the different bases. Now coming back to that NCERT page, and also to give you some general idea of basicity for all these different amines. As I said, that better to go by pKa values, right? That I will add in the notes and I will share. Don't worry, I'll get that copy very easily from this Claydon, and I will add it in notes, so you will get there. Okay, and from there you can use it if required to compare. Okay, so coming back to what we were doing, so basicity wise I think we are done, but मुझे वो NCERT वाला एक चीज और डिस्कस करना है. So I'll go back to the NCERT thing. Yeah, in nitrophenols, I wanted to tell yesterday also, I forgot, I guess, that pKa of nitrophenols, when 2 nitro are there, dinitro, then only they will be able to displace CO2 from NHCO3. 1 nitro if is, then it is not sufficient. Orthonitrophenols, metanitro, paranitro, their pKa is lesser than H2CO3 pK1. So they will not act as CO2 liberators, but dinitrophenols will act as CO2 liberators from NHCO3. Taken screenshot. Going further, I was talking about amines. Seeing these data, Now, there is some very important conclusion that you have to see. We have compared 1 degree, 2 degree, 3 degree. I mean, that is done. If you see these benzenamine is nothing but aniline. Aniline value is 9.38. Okay, when one CH2 is added in between, then it is 4.7. Right? This is what here, what values are given is pKb. These are pKb values. So if you see this PHCH2NH2, okay, if I talk of pKb from here only I'm talking is 4.7. Of ammonia is 4.75 here, 4.75. Of CH3NH2 is 3.38. Okay, so CH3NH2 is a stronger base, then PHCH2NH2, then ammonia. Then you will say, ki, what is there to keep notice? This you will justify that CH3 is having one minus I, so this is going to be a weaker base. Well and good. But how will you justify this? That PHCH2 is a stronger base than ammonia. Here pH minus I is not that important. Okay, so this is an important order. CH3NH2, then comes the PHCH2NH2, then comes the ammonia. Is that all good? Then rest it is as expected that more the number of methyls on nitrogen, it will act as a better base. So this is a stronger base, PHNME2, then PHNHME, then PHNH2. That is fine. There is no other exception, but this table, I would suggest you to go through all such acid-base tables from your NCERT in phenol chapter, in carboxylic acid, and in amines. Okay, these tables, study them meticulously. They will generate questions for mains and certainly in advance. 2017 advance was not specifically from this, but 2019 advance was from NCERT, this acidity order, right? So our total acidity basicity is done and I'm on target. First half given to this. Next half we will go to tautomerism. I'll just open for questioning. Anyone wants to ask any question related to acidity basicity, please raise your hand. I'll let you unmute and then you can ask. Then I'll start tautomerism. Any doubts? If there are, please ask. I don't see any hand raised, so I assume all done. Good, very good. So then let us move to tautomerism. Not even a single hand. Fine. Anyone else? No, no one is there. Okay. So no doubts from acid-base theory. Wonderful. So let's now start the second part of today's lecture, that is tautomerism. Tautomerism is a type of structural isomerism. It is also known as desmotropism. The word is derived from tauto, meaning the same, and meros is the part, like isomerism. Iso is similar and parts. Here it is same parts. Somewhere from that only they are deriving this name again and again. The word was derived from Greek language. In English, tautomer means rapid interconversion. In absolute English, nothing related to just chemistry. It simply means anything that is rapidly interconvertible is called tautomer. Okay. Spontaneous interconversion of two functional isomers, usually with the change in position of an atom, is called tautomerism, and the two functional isomers are called tautomers of each other. When the two functional isomers, other definition, are in state of dynamic equilibrium with each other, in liquid or in gaseous phase. In solid, all atoms will be blocked. So then you cannot have their interconversion possible. And thus, you can isolate the two tautomers when they are solidified. If you change the physical conditions, if you change the surroundings, then definitely you can isolate the two tautomers. Okay, so that is the way. Through solid you can. So other in liquid or in gaseous phase, then the phenomena is called tautomerism and the structures are called tautomers. बहुत बढ़िया. So that is the general introduction to the term tautomerism. Now let us go to what are the different type of tautomers observed. Now, if I talk to what are the different types, then just remember these are examples I am taking, and then we will limit ourselves to ketoenol tautomerism. There are several, but I am limiting myself to only triad systems. Okay, there are cycle, open chain and cycle tautomerism. There is a possibility of diet tautomerism, which is present only in HCN, HNC, HCN tautomerism. There are, but I am limiting myself to triad tautomerism. Now, what is this triad tautomerism? That is the atom is shifted or is exchanged from first position to third position to first position. Then it is called triad tautomerism. Okay. Now, talking about this triad tautomerism, there could be so many examples. First, I am talking of is ketoenol. Very basic, है ना? Ketoenol tautomerism. In case of ketoenol tautomerism, certainly you know that CH3, I'm taking example of acetone, does not mean that only ketones will have this. है ना? You will have it in aldehydes also. So this type of tautomerism is there. And where will the equilibrium will ultimately dominate? Entirely based on delta G. And delta G is dependent on delta H minus T delta S. Delta H, difference of energies. If I compare the bond dissociation energy and BDE, which are broken here and are formed here, this CH3C is same, but what are the bonds changed? CC is changed, C double bond O is changed, and C single bond H is broken. Against that, what is formed here? C double bond C is formed, C single bond O is double bond O is becoming C single bond O, and CH is now changed to OH, right? These are the new bonds formed. Now, if I talk of these are the new bonds formed, what is the dynamics? What is the value, I would say? So CH is 414. I'm talking in kilojoules per mole. 414 kilojoules per mole. CC is 347 and CO is 741 kilojoules per mole. Here C double bond C is 611. C single bond O is 351. C double bond OBDE is greater than 2 times of C single bond OBD. 351, 741. Coming to OH, it is 464 kilojoules per mole. If you add this up, it is coming to 1426 kilojoules per mole. And if you add, it is coming to 1502 kilojoules per mole. So this is thermodynamically more stable and therefore the equilibrium goes backward. ठीक? So keto forms are usually, I cannot say always, are usually dynamically more stable than enol form, and therefore keto forms dominate at equilibrium. But of course, there may be certain cases where enol may dominate over keto, but then there has to be some thermodynamic reason. It is not like just I like it and I get it. Okay, that is not possible. That like in get it wali cheez nahi hai, but in keto phenol, right? In keto-phenol tautomerism, of course, these are two different functional groups, ketone and enol. So they are functional isomers also. If I talk of keto and phenol like this type, then here I will say enol dominates because of its stability. My stability factor will go everywhere by the bond dissociation energy. I will fail at nitroso-oxymino-tautomerism. Nitroso-oxymino-tautomerism. Here I will fail. Here I will fail. I means CH3 N double bond O. This is nitroso form. And CH2 double bond N OH. This is its oxime form. Nitroso form. Okay. So everywhere it is that by bond energy, I can say this side it will dominate. Here I cannot. If I talk of here bond energy, same way. CN N double bond O single bond H. C single bond N is 293 in some books and 305 in some. But I took both and I could still not end up to what we want. 607. CH is, we didn't take OH here, it is CH. So here CH bond is broken, which is 414. If you add this total, it is coming 1314 to 1326 kilojoules per mole. Taking this into consideration, 1326. Here, what bonds are formed? C double bond N, which is 615 kilojoules per mole. I don't want you to remember the data, just to make a very clear impression on your brains. I'm writing O and H if you see. And here again, you can see that N single bond is 201 kilojoules and N double bond is 607. How strong N double bond energy is? OH is 1280 kilojoules per mole. So if I, not 1280, 464. 464 kilojoules. If I total, I'll get 1280 kilojoules per mole. So by that logic, this should have been more stable. But there is an exception here. It is an exception. I would say till now reasons not clear, but exception. Oxime form is more stable. Oxime form is more stable, and that is why nitroso always gets converted to oxime, right? Beckmann rearrangement, you talk of this, you never convert it to nitroso, is more stable and dominate at equilibrium, right? So that was nitroso-oxymino. Similarly, we go further. There are so many. I'll not go to each and every, but nitroacide tautomerism. Now, in case of nitroacide, we see nitro group dominate. Here, acai is CH2 double bond N OH coordinate O. This is acai. This is nitro. And it is found that equilibrium goes to this side. This is found to be stable. Here, this was found to be stable. Okay. Here, this was stable. Here, this was stable. Clear? So this is found to be more stable. Similarly, if I take one last, is imine in amine tautomerism. Tautomerism. Imine in amine. So what is imine? CH3, CH double bond NH. It tautomerizes to CH2 double bond CH single bond NH2. And here, like enol, imine is more stable. Okay, by bond energy, you can prove all good here, no problem. Imine is more stable. Similarly, for amide imidol, amide is more stable. Okay, those are the usuals. But one more similar example, the name is not that important, but as I just mentioned, amide imidol. This and tautomerizes to this. This is more stable. Both are aromatic. Don't worry that this is not aromatic. It has a lone pair and will have resonance. It is aromatic. Both are aromatic. And if both are aromatic, then amide is more stable than imidol. Okay. So these are the different types of tautomerism. And remember, tautomerism is very much different from resonance. Tautomerism is different from resonance. In case of resonance, what was happening? That all those structures were imaginary and only hybrid exist. You can have no resonating structure ever isolate or study. Whereas in tautomerism, those structures are real. They will be affected by physical conditions, right? If you change the physical conditions, equilibrium will shift from here to there. So it will definitely have a very strong impact. Is that absolutely clear? ठीक, so tautomerism and this resonance are different. Is that okay? No problem. Moving further. Now let us go to mechanism of tautomerism. What will be the mechanism? Now I am limiting myself to ketoenol. So heading maybe I am changing. Ketoenol tautomerism. Yes, it is catalyzed by both acid and base. Okay, it is catalyzed by both acid and base. Mechanism of ketoenol, it is catalyzed by both acid and base. So it takes place in neutral medium also. Yes, ideally it can, but extremely slow procedure as these polar bonds will shift gradually. And yes, there is a possibility, but slow process, slow interconversion, very slow. And here you can isolate them as it is a very slow interconversion. Okay? If I talk to number 2, acidic medium, that how it interconverts in acidic medium. Let me take example of acetone. So CH3CO CH2H. In acidic medium, always fixed. This H plus. CH3COH positive, single bond CH2H. This H plus is gone. CH3COH double bond CH2. Enol is formed. Now here enol is formed through carbocation. Whereas if I talk of basic medium catalysis, okay, again I'll take acetone only, then it goes through plus OH minus, attacking like this, CH3CO CH2 minus. And again, it can take resonance, CH3CO minus double bond CH2. See, O minus and CH2. CH2 is a better base. So definitely reaction will go backward. It will attack water and neutralize. But what if this attacks as a base and we get enol? So yes, you can get, but in both mechanism, it is very clear that equilibrium will go backward in usual conditions. Why here? Because see, again, if I compare O attach H and C attach H, which is more acidic, this is more acidic, right? So it will go backward. When here it can slide down to forward or backward. So OH is more acidic, it will go backward. If here I talk as an intermediate enolate, then I'll say C minus is more basic. Okay, if C minus is more basic, then I will take attack of C minus as a better base. And thus answer is ketone again. So equilibriums are always going backward for all these interconversions. Is that obviously clear? Right. But by here we assumed that alpha hydrogens, and when I say alpha hydrogen, it could be deuterium, it could be tritium, will be must, या rather will be क्या, are must for molecule, are must for molecule to show tautomerism. Right, this is a very standard thing that is true. I want to modify it, or any such alpha or gamma or further, which when form anion can resonate to C double bond O will show tautomerism. इसका क्या meaning है? What is this second line I want to mean? That any such system, for example, if I am given, need not to be exactly alpha, but CH3, CH double bond CH, single bond COH. Now this is alpha, this is gamma. But yes, it can show resonance, as I will remove CH from here and anion can have resonance. So CH2 double bond CH, single bond CH double bond CHOH. This is also a tautomer. So tautomer is exhibited from any further position. We cannot use certain types, vinylic, phenylic, and bridge head hydrogens cannot participate in tautomerism. These are only which we cannot say that are suitable for tautomerism, but others you can. Now let me exemplify what I want to say. Vinylic. So if I have CH2 double bond CH, single bond CHO, no tautomerism. Okay, if I have, say, now phenylic is like quite impossible. There is no alpha H here. But if there is ever any possibility, then it will not participate. Bridgehead. For example, if I have this system, then yes, there is a hydrogen here, but it will not form the tautomer as the bridgehead cannot acquire planarity. Okay, so these are those which will not participate in tautomerization. Others will certainly do. Still, if they do, I'm not saying that they are forming exceptionally stable enols. That depends. That depends from molecule to molecule, condition to condition. But yes, this is how first type of question says this only, that which will form enol. So that type of questions you can deal with this, right? Next, let us go to what will be the impact of tautomerism on what will be the concentration of enol tautomers in case of different molecules. So very important, very confusing, I would say, is enol content we are talking. So next heading, which is quite confusing to lot many, is enol content. For enol content, I will ask you to approach systematically. And when we talk of enol content, what is it that we are considering? Let us see. This is what I am considering. In enol content. I have taken this from Jerry March. This data is from Jerry March. So let me take it to my enol content page. Right, this is what I want. So what is the enol content? That how much is the percentage enol at equilibrium? Now see here, acetone has an enol of 6 into 10 to the minus 7, whereas acetaldehyde has 6 into 10 to the minus 5. Okay, cyclohexanone has 4 into 10 to the minus 5. ठीक? In point 2, kindly unmute yourself and let me know what you're saying. I could not understand. In point 2, clarification, PDF, tautomerism is not raised hand. Can you please explain what you are asking? Unmute yourself. I could not find you, and I think you could not unmute yourself or what? Okay, I'll continue then. If anything else, again, ask me in the end. Okay, so I was saying that look at these values, how it is shown. What are the values shown here? From here, we are talking of individual carbonyl systems and their enol content. So when I talk of percentage enol content, I mean in a keto and enol tautomerism, what is the percentage contribution of enol versus keto? Here I am talking of this enol content percentage. Okay. Now there is no fixed rule that you can say that always like this or that, but let me split it or simplify it for you. So first we will just discuss case of monocarbonyls. Monocarbonyls. Now in case of monocarbonyls, usually though of course we have said that keto dominates. You can see the value of these enol is like 10 to the minus 5, minus 6, minus 7 order. So it is very, very low, extremely low. But still, if we need to compare, how we can compare? So see, for acetone, if you check, then CH2 double bond C, OH single bond CH3. And for aldehyde, if you check, it is CH2 double bond C, OH. Now fill the data. Acetaldehyde, 6 into 10 to the minus 5 percentage. And for ketone, it was 6 into 10 to the minus 7 percentage. So the carbonyl bond dissociation energy in aldehyde and ketone is not identical. That you need to remember. Okay, it is not identical in both. For example, ketone has higher bond dissociation energy than aldehydes. And this is why you can see the difference. So in general, if I say enol of aldehydes will be more than ketones, but again, I cannot say everywhere, but this is a general thing. CH3 group jo hai na, this stabilizes the carbonyl, and overall this enol is not that stable. So thereby reaction goes backward. Okay. And thus ketone has higher, aldehyde has higher enol than ketone. Yes, but if you compare amongst aldehyde, or you compare amongst ketone, then please make it very clear, hai na? Amongst aldehyde cases, more the hyperconjugation, in enol, higher will be enol percentage. And let me exemplify from here. See butanol. Where is acetaldehyde? See acetaldehyde. Acetaldehyde enol, alpha H0. Okay. Butanol enol. 1, 2, 3, 4 double bond OH. है ना? Enol of butanol. How many alpha H? 1, 2. I'll say alpha H is 2. What is the percentage enol? Check. 5.5 into 10 raised to power minus 4. Right? If I go for CH3C, CH3H, CHO enol. Here it is. Yeah. 1.4 into 10 to the power minus 2. Here enol is 1.4 into 10 to the power minus 2 percentage. And alpha H will be 6. But provided that you are talking only of aldehyde to aldehyde, ketone to ketone. Right? If we'll jump here and there, then we cannot say that this will be valid. Let me continue for ketones. If you talk for ketones, let us say acetone, alpha H were, how many alpha H were there for acetone? CH3C OH double bond CH2. So alpha H3. Enol percentage was 6 into 10 to the minus 7. Let us go to cyclohexanone. Cyclic systems have higher, 4 into 10 to the minus 5. What will be its enol? OH, alpha H. If I ignore OH, 1, 2, 3, 4. 4. Enol percentage is increased. Okay, that is what I'm saying. But comparing always amongst ketone. Okay, never jump from aldehyde to ketone or ketone to aldehyde. That is fixed. So 4 into 10 to the minus 5 in case of cyclic. ठीक, एक जनरली कमेंट में बोलती हूं कि साइक्लिक ketones always have higher enol than open chain. ओपन चेन की कंपैरिजन में ऑफ कोर्स रिंग स्टेबल होनी चाहिए, इट इज बेटर, और उसका एक प्रोबेबल रीजन होता है दैट दिस फॉर्म इज मोर स्टेबल देन दिस फॉर्म. Why? Because here it is a log structure, so resonance is better. Here rotation allowed, so resonance may not be as good as here. So I can say Ka of cyclohexanone is also greater than acetone. That is also an added thing. Now come to further. This is important conclusion. So acetone has enol weaker or lesser. This PHCO, cyclopentanone has 1 into 10 to the minus 6. Cyclohexanone has minus 5. See, less because strain in the ring. Okay, butanol, okay, minus 4, better than all ketones. ठीक, aldehyde, we are moving, improving. pH to CH, I'll add how it is. But see ester, normal ester, no enol found. When it is normal ester, yes, when there is active methylene, then it is a different case. There are some enols, but still you can see ester percentage is 8.4. Both side ketones percentage is 80. PHCOCO 89.2. See the increase in percentage. And if both side ester, at least there is enol, but the percentage is minus 3. Right? So this should be very clear that this is not, esters do not form enol that effectively. Okay. So moving further, this was about monocarbonyls. Everything depends on the stability of the conjugate. If that a conjugate, I mean the enol form. If it is stable, then well and good. So cyclic systems we have discussed. Let me make it point number 2. So point number 3, I will say that a non aromatic keto when gets converted to aromatic enol. If it is so, then enol not only increases but also dominates. I think all of you agree to phenol thing, right? That yes, it is the phenol which will dominate, right? And there are so many cases, but it has to be a conversion from non-aromatic to aromatic. It could be a case of para-tautomerism when the migrating atom is from para position, right? Yes, that is also possible. You can have cases like this. Now see, the enol formed has that aromatic cloud, and here I have lost 3 ketones. So these are almost 50-50 percentage both. Otherwise, always the aromatic one dominates, but not here. These are very close call. Okay. If there is something which is further adding to repulsive forces, and if it forms the enol, it is becoming stable, enol will dominate, and so many more. But again, it should be suitable for possibility of such enol formation. है ना, aromaticity होना चाहिए. Now comes to next factor, that is sometimes steric factors can play the role. Steric factors lock the enol, okay, from converting. Lock the enol from form, making it kinetically stable. I'm not saying it is stable, but yes, kinetics will support it. What is it? See, not every time this will be, but if I have something like this mesitile system, now this is alpha CH, and this is connected to CHO, but this carbon is totally covered from upside downside by these two mesitile systems. Okay, so when it gets converted to enol, if I even convert it to enol like this, double bond CHOH. Now see, here the bond angle was 109 degree 28 minutes, and here the bond angle are 120 degrees. So these bulky groups are apart, and now it is better stable. Plus now this thing will have something called SIR. This bond will have steric inhibition of resonance. It cannot be participating in resonance anymore, right? So that is not my supporting factor. But once this is formed, it is very difficult for H plus to attack on this, because it is shielded from both upside and downside. Okay, this carbon is shielded, and this is why it won't form enol. So this is a general case whenever you have this type of shielding of alpha position, then steric can be responsible. Now, fifth observation is when there is a generation or extension of resonance. Okay, so it was either not there, there was no resonance. For example, CH2CHO. Now, when this forms enol, resonance is generated. So yes, iska percentage enol increase हुआ. I cannot say it will dominate on this or not. है ना? I can use this thing for say comparison of enol of this and this. Now this is already resonating. So if I am asked enol of A and enol of B, then I'll say enol of A will be greater than B. This is all I can say. Now here already resonance. Na? So example number 2. If it is COCH3 versus PH, CH, PHCH. So this is A, this is B. See, here resonance already, here resonance already. Carbonyl is already member of resonance, but here carbonyl is not member of resonance. So enol of B greater than A. Okay. In fact, this B is having 9.1 percentage enol and A is having 1.1 into 10 to the minus 6 percentage of enol. Okay. So that is how it is used. Point number 6. Strain in the ring. Strain in the ring. As I have just shown you from that data, that keto, cyclopentanol, and cyclohexanone, right? A, B. So again, enol of B is greater than A. Correct? Because 2sp2 in 5-member ring is unstable than 2sp2 in 6-member ring. Is that correct? So these were all comparison of monocarbonyls. Now I'm going to dicarbonyl. Dicarbonyls. Now dicarbonyls I'm again dividing into two. 1, 2 dicarbonyl. Okay. 1, 3 dicarbonyl or others. Others matlab 1, 4, 1, 5, 1, 6, etc. So these are same as two independent monocarbonyls. इनका इससे ज्यादा कोई यूज नहीं है. These two we will see. So first, how to write? I'll write like this: 1, 2 dicarbonyl. Now, as I have already shown you, C double bond O is bond dissociation energy is high. In case of 1, 2 dicarbonyl, conformation decides enol. Okay, conformation decides enol matlab if my dicarbonyl can rotate to this transoid. Okay, now I have two choices. This is like cis. I cannot use the word cis because the rotation is allowed. And this is like transoid. Now there is a high dipole repulsion between the two adjacent carbonyls. Okay, this high dipole repulsion makes cis structure unstable. So it has two choices, either to go to transoid or can go to enol. But as you know, enol is thermodynamically less stable, right? So there is no need to go to this side when you have a rotation and maintaining this. Of course, this will be somewhat, but no need to compulsorily go into this. Okay. In fact, if I have a logged in cis conformation, if I have a logged in cis conformation arrangement, C double bond O, double bond O. Now this cannot rotate to transoid. So it has only one choice. It has to go to enol. And this is logged in cis conformation. Okay. Now here it is 99% enol. When it is logged, it has no choice. It will form only enol. That is the only choice. Okay. Second comes the 1, 3 dicarbonyl. This I think all of you remember. Acetyl acetone is the case. Acetyl acetone forms enol like this. Okay. 76 to 80% enol content is there. Why? Reasons. So there are three reasons. First, you will say presence of active methylene group. and more the acidity of this active methylene group, more will be the possibility of enol. Second is the generation of resonance, generation of resonance in enol. And third is intramolecular H bonding in enol. These are the three factors which create this stable enol. And this intramolecular H bonding in enol, I would say 6-membered. Right? This is a 6-membered chelation which is stabilizing the enol. But definitely, as I said, first thing you consider is these two. This is like least of all. This H bonding factor is least of all. It is not the primary or the important factor. Okay. So if I am asked, like, what is the order of usual, then I'll say enol content of active methylenes I'm talking, pH, CO, CH2, CO, pH will be greatest. Then there will be one pH case. Okay. Then there will be H. Then CH3, CO, CH2. Then of course CH3, CO, CH2, CO, CH3. Right? Acetyl acetone. Till here I am talking all of pure aldehyde and ketone, pure carbonyls. Now when you start talking of esters, content will go down. And if I can talk of this one, the content is very low. Till one ester linkage, we had still some content. Where is this? One ester. We had 8.4 and two esters, -3. Okay, that is what I have just mentioned, how to take this into consideration. So this is what your enol content is. Okay? And 1,4 and further is of no importance. So we'll leave on that. Now, factors affecting tautomerism. What are the factors which affect tautomerism? So first factor, as it is a equilibrium, of course, temperature. Second, concentration. Concentration of molecules sometimes, again, I will not say always, but yes, can affect sometimes, because some of the keto can form a micelle, what you call in that surface chemistry, na? They club together and they change the concentration. And then the entire thing goes. The order becomes, the K equilibrium effect gets affected, and we have a different concentration of enol. So concentration of the molecules can have the impact. That is one possibility. Okay. Then there is solvent. Solvent is mainly useful for 1,3 dicarbonyls, not always. Okay. For 1,3 dicarbonyls, this is useful with increase in solvent polarity, keto form will increase. Will increase. So this is for 1,3 dicarbonyl, no impact on, I would say no important impact on 1,2 dicarbonyl. There it is not of any such importance. Okay? So temperature, concentration, solvent, these things can have some impact on the tautomerism. Okay, and certainly the stability of the relative stability of enols is there. That we have already discussed in detail. Now we are talking about same molecule having impacted, then what we can say. I hope this part is okay. Now we are moving to what will be the effect of tautomerism on properties of molecules. effect of tautomerism on properties of molecules. That is our next and the final topic for tautomerism. Now, what impact we can have of tautomerism? So, सबसे पहला impact, exchange of alpha hydrogen with deuterium. That is the one type of question you all must be remembering. CH3COCH3 when placed in D2O, whether in place of H plus or DO minus or HO minus, whatever, you will have CD3 COCD3 formed. Okay, so they will ask you question number of H exchanged. Answer here is 6. Is that clear? That is what you have to do. How many H are exchanged? So many questions I think all of you might have done. See, here I am having a change. Now, if this is the one, as I have told you, all possible hydrogens which can go resonance to carbonyl. So, these are my all hydrogens which will be exchanged. So, number of H exchange for this will be 1, 2, 3, 4, 5. Answer 5. Okay, this you have to be clear that all H which can participate in resonance will be exchanged even when they ask for acetyl acetone. Then 1, 2, 3, 4, 5, 6, 7, 8. Answer is 8 hydrogens are exchanged. Okay, 8 hydrogens are exchanged with deuterium when placed in D2O. That is our property number 1. Property number 2, or the effect number 2 which will be influenced, is loss of optical activity of alpha chiral carbons. Alpha chiral carbons. If there is a alpha position chiral carbon, then through tautomerism, it will lose its purity, right? It will again go to same MECH-ETCHO. So I may start with assume dextro, but I will end at dextro plus levo, racemized. That center is now racemized, provided it should be alpha to the carbonyl. Okay, if it is not alpha to the carbonyl, then it will not be racemized. That is a point you need to remember. Like for example, if I am given CO, Me and pH, this is Me and pH. Now they say what will be the product? So I will not have a racemized, I will have a distereomer mixture, because this will change R and S, but this will remain fixed. So only alpha are the one which lose their purity. Others do not. So taking into that consideration, you have to answer. Next is the isomerization of carbonyl molecules. Of carbonyl molecules. What I want to say, like CHO, CH2OH, now it forms enol, double bond CHOH. It can go to PHCOHH, CHO. See, they are all different functional groups. This is first, this is second, this is third. And all different functional groups, they are all tautomers of each other, ultimately functional isomers of each other. Right? So There is interconversion of carbonyl molecules, functional. Functional group can be changed, chirality can be changed. So many different effects could be there. A glucose can be converted to fructose through this particular process. Okay, that type thing we are saying. And I can't say just that. If I am given D-glucose, which is right, left, right, right, H, 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 H. And I place it into alkaline aqueous conditions. So I will have a change in the chirality of this, and I will have functional group also changed. So what will be formed? Will it be D-fructose? I started with D-glucose. So here in product mixture, what will be there? D-glucose, C-D-mannose, or D-galactose. What will be there? So answer for this question is A, B, and C. 3 products will be there in the product mixture, right? Through the interchange. Now the fourth property is, you can say, halogenation of alpha carbon, right? But remember, whenever this halogenation is done, either it is in alkaline conditions, X2, then you can have trihalo. But if it is in acidic conditions, then it is only monohalo product you will form, not the dihalo. Okay, there is a question in 2016 JE on this haloform reaction. Correct? Then you will not have any further reaction. Only till here you will form. Fifth point is halogenation of alpha carbons. Now, if I talk of halogenation of alpha carbon, how I can achieve? For example, if I have acetone, I treat it with some base. Let it be NaH. So I have CH3CO, CH2 minus, and then I treat it with some alkyl halide. So I can have CH3CO, CH2R. So this halogen I have introduced at alpha position. Very good. But if there is a substitution like this, then there, as the tautomerism is entirely reversible, if I take a bulky base, okay, bulky base will fail to attack this hydrogen. It will attack this hydrogen and followed by MEI. Then I will have this as a product form. But if I take a smaller base like NH and then I attack MEI, then thermodynamic control enolate is formed, and here you will have the alkyl halide introduced. Alkylation, this is very important. Okay, this is bulky. So this is forming KC enolate, kinetic controlled enolate, and this is forming TC enolate, which is thermodynamically more stable. That is formed. And the last effect of tautomerism is its reaction with NNO2 plus HCl. I think all of you must be aware. CH3COCH3, CH3COH, double bond CH2. So with NNO2 plus HCl, what is this? They form NO plus. Whenever there is attack of any electrophile, you have to use enol. Nucleophile, take ketone. So CH3, C double bond O, single bond CH2 NO. Now we have just discussed this will always be in equilibrium, right? Nitroso will not be nitroso, and here so it is further active methylene like this oxymino. Okay, it will be in this tautomeric form. So you will get this as a product. If you hydrolyze H3O plus, if you put hydrolysis, then see this will undergo hydrolysis and you can have a new carbonyl form adjacent to existing carbonyl. Okay, that is how you can use tautomerism for the reactions. In short, I will say always when you have to use nucleophilic attack on carbonyl, use its keto form. And when you have to use its attack of electrophile on it, then use its enol form. That is a fixed thing. Okay. So that brings us to the end of tautomerism. Tomorrow I'll make you revise entire this what you call chemistry in everyday life. So it's a time for doubts. If anyone has any doubt, please raise your hand. Others can start leaving. I'll share my notes to central office. And if you want, ask your vice principal, principal or dean sir to request from central office. You can get these all notes from day one only. Okay. I'll send these as a copy to central office. Okay. So anyone with any doubt? So I have Ibrahim. Yes, Ibrahim, just I have allowed you to unmute. Please ask.
Ma'am, Tautomerism's the sixth point. I couldn't catch it actually. If you
Tautomerism,
would please. Sixth point.
6, na?
Yes, ma'am.
That effect thing? This one?
Yes. No, ma'am. Previously, like a few
Okay,
slides earlier.
I'll move backward. Stop me wherever you need, okay?
Okay.
So, see here, no. Let me move backward. 6th is this. Here also I wrote 6. Ibrahim, is this the point?
Before,
Okay.
a bit more
Let
prior.
me move further. Okay, in all, then going further. This one?
Yes, ma'am. Yes.
Okay, beta. So I said, Ibrahim, here that here if you see, this is stable aromatic system. Already it is aromatic. Are you comfortable with the idea that this is an aromatic structure?
Yes, ma'am.
Right. And this is also aromatic. Now, in general, if we are talking of amide imidol tautomerism, CH3COH double bond NH2, then by bond dissociation energy logic, amide dominates.
Yes, ma'am.
Right. Now, see, this is also amide imidol.
Mm.
But
Yes.
your system is already aromatic. So there is no driving force. Why should I lose my bond dissociation energies? That
Yes,
is
ma'am. Okay, ma'am.
it as stable. One more thing,
Thank you.
students, others also, please wait. One thing, while just changing the slide, I would like to add. Where should I add as a, okay, I'll add as a next point. That as there is equilibrium in entire mechanism, equilibrium in entire keto-enol conversion, right? Keto-enol conversion. Therefore, KC-TC effect will be applicable. Okay, let me exemplify fast what I want to say. CH2, CH3. See, for example, if I talk of basic medium, I will get CH2 minus COCH2 CH3, and I can get CH3CO CH minus CH3. This is 1, this is 2. If I'm asked which is more stable, I will say 1 is more stable than 2. Why? Less plus I. Ashish, just give me 2 minutes. I will ask you to unmute. Just wait, beta. So this converts enol like this, and this converts into enol like this. So let me name it as 3 and 4. So 4 is more stable than 3. Why? Hyperconjugation. Now see, more stable enolate is forming unstable enol, right? So what I wanted to say is this is Kc enolate, this is your Kc product. This is your Tc, thermodynamically controlled enolate. This is your Tc product. So irrespective of medium, if it is given, then always Tc will be major. Because these are just catalysts, na? Irrespective of, in very old Jerry March, it used to be there that in acidic medium, you will have Tc product, and basic you will have Kc, which is inappropriate. They themselves have removed in their latest editions. Okay, so in both mediums, Tc product will be major, provided temperature heat is sufficient. Only under very low temperature conditions you can have Kc enolate, otherwise not. Okay, yes, Ashish, now you can unmute yourself and please ask.
Ma'am, in the aldehydes and ketones, in aldehydes, the enol content is more. Can you say, when compared to ketones, when you say the reason of the...
Bond dissociation energy.
Okay.
The bond dissociation energy of keto bonds. Here we studied this point, what Ashish is asking. That as I said, na, that ketones versus aldehydes enol content. Aldehyde ketones higher. So it is the bond dissociation energy of carbonyl bond, and I want to add the value for your reference. Okay, bond in acetaldehyde. Just let me give you that energy if I could get. Tomorrow I will give Ashish because there are so many pages open. It is like difficult to find. But I have in some of my detailed notes somewhere. Tomorrow I will definitely add it. Okay.
Okay, ma'am. My next doubt is in first point, properties of tautomerism.
Application of tautomerism, beta.
Yeah, yeah.
Wait,
Yes, ma'am.
wait. Let me go there. Somewhere here.
Yeah,
Check.
first point. Yes, second example,
Yes.
hydrogen with the sp2 hydrogen. Why
How it is
sp2?
gone.
Huh?
How it is gone. Right?
Yeah, yeah.
See, beta, when you will have base attached, let us put the answer here. Okay. So when this base comes, if I remove this H, then no problem.
Yeah, no problem.
Right? So first I am removing this H. Okay, what will I get? I will get minus double bond, double bond. No, not this is not a double bond O, right?
Yes,
So
ma'am.
here 2H justified.
Okay.
And the other enol, this side, this 2H are justified. Now see, this has a resonance, na Ashish?
Yeah, yes, ma'am.
So here also there will be exchange with D2O.
Okay, I understood.
Now you understood?
Yes,
Again,
ma'am.
DO minus or OH minus, whatever given. So bond energy wise, this will go. Anna? Where is my double bond? Like this and so on. Okay.
Yeah.
So that is it for Ashish.
Yes, ma'am. Thank you.
Okay. Thank you, Bete. Feasty, that is the name I can see. I guess this is not your real name. So Feasty, yes, unmute yourself.
Ma'am, I had the same doubt between aldehydes and ketones. When ketone forms enol, the alkane it forms will have more number of alpha hydrogen. So
That is I said that in the lecture, beta. Let me
Yes,
re-add. Right? I said that you can use that hyperconjugative stabilization only when the functional group present in them is same. If the functional group present in them, like aldehyde and ketones are different functional isomers,
yes, ma'am.
so you cannot use them for direct comparison, hyperconjugation directly, because why you cannot use beta? Because when you break a bond, the thermodynamics involved will be different. Right? So if a ketone has a higher bond dissociation energy than aldehyde, then for the delta G thing, you will need more energy.
Okay, ma'am.
Okay? More energy will make that equilibrium lesser. I'm searching where I have written energy. Data I have written somewhere, but I'm missing. Tomorrow only I'll add. I'm really
And
trying to.
ma'am, can you
Hmm?
explain how change of concentration and change of temperature affects the tautomerism?
Yes, I can. I can. Wait, where was it? Backward. See, temperature, though, as we have seen, that bond dissociation energy, for example, keto BD was higher than enol. So I can say that delta H for this ketoenol tautomerism is positive. Right? More energy is consumed than the amount of energy released. Do you agree with that?
Yes, ma'am.
Right? So if delta H is affected, then you know na ki delta G affected, then delta G will be affected. And K is equals to A e to the power minus A by RT. And delta G is also affected by K. Forward, backward. Or I can further say Le Chatelier. Delta H positive. If I change the temperature, then as per the Le Chatelier, the direction of ketoenol will shift. That is why. And concentration is not for always, but for certain cases, what happen that when we put some n number of molecules, then they cluster like this. So I might have added, say, 10, but they are behaving like 7 or so, something like this. And any equilibrium is always affected by temperature, na? Sorry, by concentration. Again, why? For Le Chatelier reasons only. That where the equilibrium will shift. That is why. Okay, but this is again limited to certain cases, not in general. Is it fine? Okay, let's go to Fatima. Yes, Fatima. Please unmute yourself and ask. Fatima. Yes, you have unmuted, but I think your mic is not working. Fatima, then how will you ask? Is there a possibility of chat? I don't see. Chats are not allowed, it seems. So if you could speak. Okay. Meanwhile, Fatima is trying to activate her mic. Others, if there is anyone else to ask doubts, please do so. And we'll wait for Fatima to unmute her mic. Okay. Fatima could not manage her mic. Fatima, you could not. Please rename yourself with your question, Fatima. In place of your name, there is an option of rename. In that your name, you put your question. Okay. Type your question as your name. I will read and I'll try to respond. Anyone else? No one? Okay, then you guys can keep on leaving. I'll wait for Fatima to write if she could. Same thing, you can ask for your notes from central office. Tomorrow we'll do chemistry in everyday life. Please sit with your NCRTs compulsorily.